Yeah, thanks for having me. And yeah, unfortunately, I wasn't here yesterday, so maybe I'm saying some things which are a little bit redundant. Also, I wasn't 100% sure about the prerequisites, so I'm just going and playing it by heart. Just feel free to interrupt me at any point, of course, as usual. So I want to first talk a little bit about the characterizations of dualizable categories. I think Sasha has already done some of those and also announced that I would do others. So maybe I do my duty here. So recall that PRL stable is the category of presentable stable infinity categories. And left adjoint functors, that's the L. And then this has the tensor product, the Lurie tensor product. That's just the universal presentable category, which co-represents by co-continuous functors. And then it also has an inner hom, which is just the category of left adjoint functors. It's the inner hom with respect to this tensor product. So in other words, if C and D are presentable stable, the inner hom is also presentable stable, and it acts as an inner hom. And then the notion of being dualizable, I mean, just means if a dualizable object in PRL tensor, dualizable in PRL stable tensor, just whenever you have a symmetric monoidal infinity category, it makes sense to talk about a dualizable object. Right? And the dualizable just means you have evaluation and co-evaluation maps between C, tensor C dual and the unit, which is spectra in this case, and then they satisfy the zigzag identities. And necessarily then the dual, which I C check, is going to be the inner hom to the unit. That's just a general fact about closed symmetric monoidal categories. If an object is dualizable, then the dual is necessarily the inner hom. And then the evaluation is the obvious evaluation. If you tensor with C, I mean, there's an obvious evaluation map to spectra. And then somehow basically what you're saying is you're dualizable if there's a co-evaluation satisfying the zigzag identities. And what I want to do first is give a characterization of these dualizable categories. And I guess I'm saying, I mean, most of this is due to Jacob, Lurie, and Sasha, and Dustin, but I don't want to, I mean, I'm happy to give a little bit better credit if you want for single points, but let me just write one big theorem. And that's, I mean, if C is a presentable stable infinity category, then the following are equivalent. The first is, I mean, C is dualizable. Second, C is a retract in PRL stable of a compactly generated stable infinity category. Compactly generated means like int of a small stable infinity category. Right, and maybe, I mean, one of the first exercises you do, I mean, you see immediately this implies that compactly generated stable infinity categories are dualizable, and one of the first exercises you do if you think about dualizable stable infinity categories is to prove that int of a small stable infinity category is dualizable. And if you haven't done that, I really recommend it. It's a good exercise in writing down evaluation and full evaluation. This is kind of a straightforward thing to do to prove that this is dualizable. And it's a general fact, so somehow the direction 2 to 1 is very easy. Once you observe that compactly generated stable infinity categories are dualizable, it's also just a general abstract nonsense fact that retracts of dualizable objects are dualizable. Because I guess you can just let the dual be the corresponding retract of the duals. I guess you need sort of retracts to exist in the ambient category, or if you have an inner hom, this is also always true. And then you just check that evaluation and co-evaluation can be written down. So 2 to 1 is actually easy. 1 to 2 a little less so. What is 3? 3 is C is the kernel of functor int D to int E, the form int F, where F, I mean D and E are small stable infinity categories. And F from D to E is an exact homological AP. And maybe I guess I should say what a homological AP is. So let me maybe sort of use this board to give some definitions. So D to E, called homological AP, if int E, the restriction int E to int D is fully faithful. That's a functor between small stable infinity categories. So this restriction is fully faithful, or equivalently, if int D to int E, that's the left Kahn extension along this functor, this is like a Bautfeld localization. But that just means it's a prior Kahn localization with fully faithful adjoint. And this is obviously the adjoint. And so this is a homological AP. And so
they're actually the same as morphisms
in the ambient categories. So I guess I sort of should be a bit careful with the board work, not to run into writing on the wrong board. So 4, what is 4? So we can even be more specific, namely C is the kernel of a functor mod R to mod S for R to S, a map of ring spectra that is a homological AP. Okay, homological AP. And maybe I should tell you now what a homological AP of ring spectra is. Homological AP of ring spectra is just, I mean, R to S homological AP. I guess you can just reduce it to the previous notion. You just say the induced map on small categories, compact objects, is a homological AP. But you just take the small stable infinity category, idempotent complete stable infinity category generated by R. Or I guess by definition this means mod R to mod S, the Bautfeld localization, which is also equivalent of course to restriction mod S to mod R being fully faithful. And I guess being a Bautfeld localization basically means that this functor, if you compose over here and go back, this is an idempotent functor. So you can check that on R itself. So this is also equivalent to saying that S is idempotent over R. So S tensor over RS to S is an equivalence. Right, that's just somehow another way of thinking about it. And maybe finally, let me sort of add one final thing, and sorry for the confusing board work. So if you let I be the fiber of the map R to S, right? So we can think of, I mean, this is Smith's ideal. So we can think of S as a quotient of R by I, and then you can also say this is also equivalent to I tensor over R I being equivalent to I. That's the almost mass situation that Sasha, I think, briefly mentioned. It's an ideal that's idempotent in R, and then you get sort of a homological AP, and then in this case, I guess it was
one more. Replacement product was push out. S push out with S. R is S.
What's this? Oh yeah, right. I guess S push out over R is S equivalent to S. Yes, I guess. Okay, does someone know another one?
So where's the push out?
In the one rings, yeah. This is like, I don't know, maybe I should write it like amalgamated style product. E1 push out.
as it's, so if R and S are all like EA rings, so this is also true.
Actually, it is.
It's
I think it's in high algebra.
Yes, I think it is true in all ENs. But I mean, I'm not so convinced about this being super useful. It is useful in terms of characterizing those in terms of abstract categorical properties, of course. I don't know how useful it is in practice, to be honest.
It's not easy to check.
Yes. And let me just say, in this case, the kernel, we will write the kernel here as mod r, I. So that's one of these like almost categories. So every dualizable category is such an almost category. That's characterization 4. Characterization 5 is even a bit more specific. So C is dualizable if C is the kernel of mod R plus mod S for R an H unit ring spectrum. Ring spectrum. It's not switch to board 2.
Yeah.
So maybe you could push up the board so that
yeah, okay.
you continue your beautiful board work, you know. So.
I know. I'm very excited myself. Thanks, Jethro. Appreciate it. So what is an H unit ring spectrum? R. R a non-unital ring spectrum. I mean, all ring spectra at the moment are E1 is called H unital. If, I guess, R plus is the unitalization. You can just add join a unit, right? So as a spectrum, it's R plus here. Same way that you learn in algebra how to add join a unit to a non-unital ring, you can also do in higher algebra, and then there's a map down to the sphere. Projection to the unit, if this is a homological equi. Right, and then you see that again, we're basically back in situation 4. Because we're just looking at this homological equi and take its kernel. And that's a dualizable category. And I guess the claim is that every dualizable category is of this form. And maybe I should say in this case we call this category, so 5 continued, we call this category this kernel of this map from mod R plus to mod S. We call this, I guess, mod H R. That's because you can think of these like this kernel as those modules over like R plus. You know, like a module over R plus for a non-unital ring is just basically the same as a module over R, because you don't have a unit, you can't impose unitality. And then it's just those modules which are non-degenerate in a specific sense, or H unital modules. Okay, so that's kind of H unital ring spectrum. That's characterization 5, it's dualizable categories. What's characterization 6? I guess I'm going to get up to 10. So the next one, oh, there goes.
Yeah, I can't see all the rings
No. Definitely not. I mean, of course, like, I'm not, yeah. And by the way, I guess in some sense, like, all directions, like 5 to 4 to 3 to 1 are like easy, right? Because everything, like, basically is a special case of the previous one. You always see that you're a regrade. The non-trivial direction is going the other way. Okay, so what about 6? Condition 6 is the co-limit functor. From int C, I mean, I call this K, from int C to C. Right, int, I mean, I hope everyone is familiar with the category int. The int category, just formal, like, filtered co-limits of objects in C, and there's a co-limit functor here. And this admits a left adjoint. Left adjoint. And we call this left adjoint J hat. So,
Yesterday was the way.
okay. I mean, I got used to JHead. Probably I'm going to mix it up if I try to switch to JHead now. To white. already happens. So somehow, I guess, I mean, this functor automatically has a right adjoint, right? Being the constant inclusion, where I consider an object in C as a constant like int object, like basically Yoneda. And then we're asking here to have a left adjoint. And this left adjoint, by the way, is automatically fully faithful because the right adjoint is fully faithful. This little lemma that if a functor has two adjoints and one of which is fully faithful, so is the other. And it's automatically a Boas decomposition. That's condition 6. Condition 7 is C is omega 1 compactly generated. And the co-limit, which I also denote K from int C omega 1 into C. That means the left adjoint. And we think of 7 as a sort of set theoretically improved version of 6, because this is an actual presentable category as opposed to this one. And note, I mean, being omega 1 compactly generated is equivalent to the right adjoint to K being fully faithful. Right, so I could sort of, I guess, package these two things together and saying this functor is fully faithful left adjoint. It would be an equivalent way, but I think somehow it's useful to know that every realizable category is omega 1 compactly generated. Okay, and so what's condition 8? And now we come to the sort of local properties of like realizable categories. This is 8 is C is generated under co-limits by what we call compactly exhaustible objects. And what's a compactly exhaustible object? I guess maybe I can push this one. This is, first of all, you need to understand the notion of a compact morphism. So I guess, what's a compact morphism? A map x to y in C is called compact. And I mean, there are slight variations of this. Let me, I mean, in our script, I guess we call this weakly compact, but let me maybe not get into the subtleties of this here. If for every filter co-limit, B equals column BI, every map Y into B, the composite, if you have a map like this, you can just go from X to Y to B, and I want to ask this composite factors over a finite stage. And of course, factoring means up to homotopy. What does this mean? Factoring over a finite stage, let me maybe write it diagrammatically. I have like x to y, and then you go to column over the di's, and then there's a di0 and a lift like this. So you have the column inclusion from di0, and you want to require a lift like this in a commutative square. And you see, I guess I learned this from Dustin, but this is of course, I think Krause and others have done this much earlier in I guess, Royal Johnston in one category land. And it's a relative notion of a compact object. Right? If you had a compact object, that mapping out of a compact object, if Y was a compact object, then this would have to already, this map would have to factor to a finite stage. pretty much the definition of like compact, at least if you ask it on mapping anima. And here we are asking a relative notion. And yes?
I would dispute that characterization on technical grounds, because for me a relative notion should be stable under rollback, but it's important to note that compact is not stable.
Right. So I think, I kind of agree. I think there's stronger notions of being compact. I think this characterization is correct that I'm going to give for the notion of dualizability. And then once you're dualizable, somehow all possible notions of compact morphisms you can like dream up along those lines will be equivalent.
But I don't think any of them are close to that rollback. So I think it's really, I
But
don't
even
know.
it's interesting. It's for the name relative. Yeah, yeah.
Wait, what are you?
I'm
You're
rejecting calling it a relative notion of compact.
Yeah, yeah.
because-
Oh, I see. Okay, sorry. Okay, sorry. No, I understand. Okay. I see. Sorry. Okay, so you're not complaining about the notion compact morphism, but about my explanation. Okay,
Exactly.
then maybe we can
Yeah.
just forget the explanation and go with the name. Okay, let me say why I was saying relative. Maybe incorrectly. Relative is because, of course, if you're compactly generated, it's easy to show that this means that you actually factor over a compact morphism, a compact object. So in some sense, you can think of it as a finite range morphism. Like if you think about like vector spaces, that being like compact in that sense would mean you factor over a finite dimensional vector space. Okay, okay, what is compactly exhaustible? That an object X in C is compactly exhaustible. If it can be written, the definition. As filtered colimit over the natural numbers, in this case, x0, x1, and so on, with all maps xi to xi plus 1 compact. Well, that's like when an object is called compactly exhaustible in here, so now I think definition 8 makes sense. We're generated under colimits by compactly exhaustible objects. And of course, we call this compactly exhaustible because of its relation to topology. I will get into that in a second. But let me maybe give another characterization, which is mine. First of all, I guess if you say filtered colimit, like it's a functor from some category, and the category has to send like identity somewhere. These are not compact. But okay, let me maybe give you what you want. I was planning to do this anyways because I keep getting this question, and I sort of started thinking about it for a bit. So here's, an object is called transfinitely compactly exhaustible. If it can be written as follows. And now I guess I need to back here. Oh no, maybe people want to see what I've written the report. If it can be written as x equal column I of xi's, where I is filtered, doesn't have a determinate object, and is what we call antisymmetric. So So antisymmetric for a category means that the non-invertible, i.e. non-invertible morphisms in I form an ideal. An ideal is just a bunch of maps, so that if I pre or post compose with any other map, it stays in this class of maps. And this means, this is just equivalent, antisymmetricity is equivalent to, maps that have a one-sided inverse are invertible. Right, so if you think about like posets, then this is satisfied, and this is exactly like antisymmetry in a poset. That's why we call it antisymmetric. And that's when we call an object.
No, but we wanted some conditions on this effect.
And this is like the category. And you're absolutely right. So I read it as such that, I guess now I sort of want to get back to Florian's complaint. Now I want to tell you what the compact morphisms here, such that for every I to j non-invertible in I, the induced map xi to xj is compact. Okay, so that's sort of the correct generalization of the natural numbers I claim, and you can think about this. This is like, if you're happy with non-unital categories, this is like exactly the unitalization of a non-unital filtered category. If you start thinking about that for a bit. Okay, so I guess let me continue with 9. Condition 9 is now every object in C is transfinitely compactly exhaustible. So that's how you say this correctly if you don't want to say natural numbers. And the last condition is AB6. We call it AB6. This is filtered colimits in C distribute over products. What does that mean? So if I have a bunch of filtered colimits over, say, some indexing categories ik, all of which are filtered, of objects x, k, I, and then I take a product over k. So I guess k is a discrete set, every ik is a filtered set, and then this is a bunch of, like, for every k, it's like a diagram defined on ik. This is what you can write down. And then distributing over product means actually you can sort of flip colimit and product, but you have to do this in a smart way. So you have to write down colimit over a more complicated category now. And this is going to be the category of sequences. Ik is going to be a family of elements in the product. K, K, Ik. Right, this is again a filtered category. You have somehow the sequences. And then you take the product, k to k. And now because I have the ik's, it makes sense to write down something like x, k, ik. And there's a canonical map from here to there, and you stipulate its inequivalence. And I guess you could more generally say filtered colimits distribute over limits. But because of stability, we somehow, finite limits are fine, and so actually we only need to ask for these products. And let me say, you could also just assume all of these IKs are the same. It's enough, because generally if you have a functor between stable infinity categories with infinite products, preserving arbitrary products is equivalent to preserving products like where every object is the same. Like an easy retract argument. Okay, these are the...
Sorry, I have a question. So you like this description. Can we replace this future system by ordinals? Because ordinals is, if I remember correctly, any future coordinate can be rewritten in cofactor.
I mean, there is a notion of cofinality. You have to be a bit careful, and I think in this...
It's not true that every future country you have this cofinality, but for the future coordinate, if I remember correctly, there is a way to replace a future system by a...
Yes, I believe you're right that somehow we can replace this by filtered ordinals here, and it's of course, as you say, not true that every filter coset has a cofinal map from an ordinal. Yeah, you need to argue a little bit more smartly. Yes, absolutely.
But in general, this process involves like replacing by colimits inside, and that's going to break the compactness, I think, of the maps.
Yeah, but I believe somehow you can, I mean, just by, I think you can just figure out that somehow the explicit construction that you give can be done by a filtered ordinal somehow. You know, because, you're not just start with any random, like, transfinite, like high transfinitely compactly exhaustion, but somehow you use this to prove somehow that you're like dualizable, and then you can write on the canonical diagram. It's like some slice style construction. So I agree that it's, I don't know a direct proof of this. I think the fact is true, but the proof is a little bit involved.
But comes to the opposite. Initially, you just consider the direct system and just require that for any I, there's J greater than I, but that sets it from my side. XJ is complex. This is also sufficient.
Because then you can write it as a polynomial, yes. Yeah, there's variants of this. I kind of like this because somehow you say it in terms of non-unity categories, it looks super canonical. I mean, if you like that or not, I don't know, but anyways. Oh, yes. Okay, I guess I'm messing up. Yeah, what's the way to rescue the sentence?
Are distributed over.
Over byproduct? Yes. Okay, this is like grammatically questionable.
And now if you rescue your horse.
Okay, so
Let's push them up again.
okay.
Yeah. Do I understand correctly that those compact maps are like a two-sided ideal or something?
Compact maps are an ideal, yes, absolutely. Yes, I was gonna give you some rough sort of statements, like maybe some indication of proofs. I guess I have until half past for it. So let's see. So I guess somehow, as I said, like the implications 5, 4, 3, 2, 1 are kind of easy. Maybe one interesting step is like if you are dualizable, how do you see that you are a retract of a compactly generated category? But that's in some sense like what gets the whole theory going. And maybe there what you do is like if C is dualizable, we can write it as a Bausfield localization. Because it's, this doesn't need dualizability. It's just because it's kappa compactly generated. You somehow have a Bausfield localization in C kappa. And what you do then, you tensor this with a dual. Int C kappa tensor C dual to C tensor C dual. And the general fact about the Lurie tensor product that it sends Bausfield localizations to Bausfield localization. So this is also a Bausfield localization. And then what does this mean? This means like, we have our co-evaluation. That's what I said, like witnesses that it's dualizable, and sort of Bausfield localizations are in particular like essentially surjective, and giving such a functor is just basically giving an object here. So you can sort of lift it here. Right, you'll find a lift like that, every 4 functors are left adjoint. And now what you do is actually, you just reinterpret this. What is a map from spectra into C tensor C dual? That's, by duality, you can just bring the C dual over. So it's a map from C to C. But which map is the co-evaluation correspond to? That's the identity. Right, and what is the map from here to there? This is the same as the functor from C to int C kappa. So what we've achieved is actually we factored the identity through int c kappa. Like this. That's just unfolding, like reinterpreting this diagram by adjoining over. But that's what we want. Right now we've exhibited C as a retract of int c kappa. That's how you sort of get this direction. Okay, so and maybe another interesting direction or statement is. No, it doesn't. It's a general fact about like the Taylor product that preserves post-utilization. And maybe another sort of interesting direction is somehow 2 to 6. So 2 was the statement that you're a retract of a compactly generated category, and 6 was the statement that this J hat exists. So confused with Y and J. Thank you, Sasha. This J hat exists, and like I guess first of all, if C is like int C naught compactly generated, then what is the J hat? So then the J hat is very easy, because then we need to write down the map from C, which is int C naught, to int C. But now you can just check that somehow you can just define J hat to be int of the inclusion. Right, and then it's very easy to verify that this is the necessary left adjoint. And so in the compactly generated case, this functor J hat is something you can really understand. Like it sort of writes every object in C as a filtered colimit of compact objects. That's what it does. And then somehow to pass to retracts, use some abstract argument. I guess let me just say it like that. You need to somehow observe that if this J hat exists for a category itself, then it also exists for retract. That's sort of a clever argument by Jacob, where you sort of get a retract of a left adjoint under certain assumptions also is a left adjoint, or like has a left adjoint, sorry. So this is kind of maybe, just wanted to mention this because it's useful in the case, to understand it in the compactly generated case. And maybe, of course, 6 to 2 is obvious, right? If you know that you are sort of, you have this map J hat, and I told you that it is kind of fully faithful, that just means I've exhibited C as int C, and I guess you need to worry a little bit about set theory. That's kind of why I brought in the 7. So you need to worry a little bit about, like this almost exhibits C as a retract of like a compactly generated category, except we need to worry a little bit about set theory, which you can do by replacing C here by C kappa arguments. And the last thing I wanted to mention is, or the last 2 things, is maybe 7 implies 3. That's an interesting direction because, 7 was a statement that we have this kind of, I guess now I'm using the that theoretically correct version, go from C to int C kappa, omega 1, the existence of this J hat, which is fully faithful. And then you want to know why the hell is then a kernel. Right? 3 was I'm the kernel of something between compactly generated categories, and that's somehow, if you have a fully faithful inclusion of stable infinity category, it is just the kernel of its co-kernel. Just a property, like, in this world. And so what you do is you just consider the quotient here, the Verdier quotient, see? That's a quotient by the non-obvious inclusion of C into int B, int C. And because this guy is compactly generated, it follows that every Verdier quotient is also compactly generated. So this is automatically int of something. And that's something we call the continuous typing category. So that's a small stable infinity category.
It makes sense to include the subject omega 1 because you can do similar stuff for rotating personality.
Yeah.
Annotation. I just included it in the subscript.
Yeah, I know. don't talk to me about notation, I'm going to be confused again. Sasha is making a good point that I haven't just made a choice here, but I believe somehow omega 1 is the canonical choice. I believe this deserves the name without a ugly subscript. And then like for other kappas, you may like add a subscript.
Yeah.
Okay.
Sometimes you just want to project some object to the kappa category. It's large, you cannot do it.
Yeah, so I guess somehow we have this thing here, right? Like so to this continuous Kiking category, this map P, and this is like a homological AP. It's just by the general theory of Faust generalization. If you form this quotient, then this is a homological AP. And that's somehow how you canonically produce such a sort of resolution of C by a sort of two-term complex. And as one last thing I want to mention, one last indication of proof, and that's why 6 is equivalent to 10. The 6 was a statement that this J hat exists, and 10 was the distributivity of products over filtered colimits. And this is because this distributivity is equivalent to the functor K from in C to C, preserving the product. Right, so if my functor is to admit a left adjoint, it better preserves all limits, because we're stable, it only has to preserve products. And then you can just write down what it means for this functor to preserve products. And the point is that you have to think for a little bit how to compute products in C. And because anima has the property that products distribute over filtered colimits, you basically get that this right-hand side here describes somehow the product in the int category. But you basically have a product of a bunch of int objects, and that will be the int object index over this filtered colimit. And so it literally somehow, spelling this out literally means this functor preserves products, and vice versa. If it preserves product, then this will be true. And then somehow you have to think for a second why it's enough that this functor preserves limits for it to admit a left adjoint. There's slight issues, right? Because int C is not presentable, but I mean you can easily overcome those here. Okay, so that's somehow why this is a useful characterization.
So that's a way to think of AB6.
Yes, yeah. Absolutely. AB6 is just literally spelling out what it means for this to preserve limits.
Even for ordinary category, even in classical category.
Yeah, I guess this is like basically due to Grothendieck and to Roku. He had like figured this already out, which I find very impressive actually. Okay, anyways, so I mean, let me sort of spell out one example. Yes, so so I guess somehow what you do is basically, if you have a compactly generated category with finitely many compact objects, how do you write it as a module category over a ring spectrum? What you do is you basically take the matrix. I mean, one explicit way is to take the matrix of all maps between the compact generators, right? So said differently, you take endomorphisms of the direct sum of the compact generators. That looks like a matrix, right? And you can also still do this kind of trick when you have like infinitely many compact generators. You basically take somehow the colimit over endomorphisms of sums of finitely many generators. And so if you're compactly generated, this way you wrote your category as some sort of modules over what's called a locally unital ring spectrum, a filtered colimit of like of unital ring spectra along not necessarily unital maps. So that's kind of what happened in the compactly generated case. And in the compactly assembled case, or in the dualizable case, what you do, instead of talking about maps, you talk about compact maps. I was going to indicate that, but sort of, you just in this kind of matrix style description, you just replace map by compact maps. And so in other words, you pick a bunch of like omega-1 compact generators, and then you take this huge like filtered colimit, this huge matrix of like compact maps between these like omega-1 compact objects. That's kind of the idea, and then you have to work with this.
Well, Tom, let me one line explanation. choose your have
Yes. Okay. So I guess.
Why get from C to input C? The image is contained as some input C0. You can assume that C0 is generated by one object.
Yes.
Then it's module super.
So okay. So what? Let me say, Sasha, of course, said that what you do is you take this resolution C by int C omega 1 to the Kalkin category, and then you write int C omega 1 and the Kalkin category basically as modules.
Not exactly. You just sum up all objects. C omega 1. You get one object.
Yes, but I think this only presents it as an almost category, not as in modules or an H unit ring spectrum.
Yeah, but then you can.
Yeah, then you have to work a bit further with it.
Can you say that in the microphone so everyone can hear?
Okay, so maybe Sasha is happy to answer questions about this after the talk. So let me just give you one example. I think Sasha has already discussed this. You take sheaves on X, where X is a locally compact topological space. Yes, space. And I guess I could and this is like sheaves of spectra. I guess I could somehow use like sheaves with value in any dualizable category. And then you can wonder, the claims, I think Sasha made this claim, and I guess maybe he gave a proof that this is like dualizable. But sort of I like this kind of internal way of seeing it. Because obviously this kind of sheaves is generated by something like suspension spectrum of the unida of U. These are like the generators of this category of sheaves, stable generators, otherwise you have to shift up and down. And then somehow the claim is that if you have a map in the category of opens, in open X, such that the closure of U, you can sandwich a compact in between. Okay, compact. Then the claim is that the induced map from sigma infinity plus U to sigma infinity plus V is like a compact map in the category of sheaves.
Actually mentioned the paper. I mentioned this
In the paper. Okay, so yeah. Yes, I mean, this is yeah. Anyway, so then U to V, sigma infinity plus U to sigma infinity plus V is a compact map. This is basically not so hard. Basically, what you do is you have to map it into a filtered colimit, and then you see mapping this into a filtered colimit which just evaluate on V. And generally, filtered colimits of sheaves are a little bit tricky. You can't just say, if you evaluate it in open, it's the same as a filtered colimit. But for compact, this is true. That the filtered colimit of sheaves evaluated on a compact is the filtered colimit of the evaluations. Right? So in order to somehow factor this map, you use that you can pull back to K. There somehow you can commute the filtered colimit out, and then you go back to U. This is kind of the rough idea why it's useful to have this K in between. And then finally, U sigma infinity plus U is compactly exhaustible if U is in the sense of topology. Right? It's a filtered colimit, natural number index colimit of open subsets, such that in between every two you can sandwich a compact set. That's a classical notion of being compactly exhaustible. And then X is any U is a filtered colimit of such. Pardon me?
But it's
Filter. Yes, exactly. The intersections of compactly exhaustible are also compactly exhaustible. That's no worry about this here. Yes, okay, and then somehow you see that then somehow every U in the category of sheaves is a filtered colimit of compactly exhaustibles, and then you see very explicitly.
But you can also assume that U is comparable to T, and then you see that it's only one.
Good. And actually, it's enough to be compactly generated. You never need it house off, by the way. Okay, so maybe I erase first.
This fact about on the compact
What is it?
The fact that on a compact space, the filter colimits being in the focal section.
Yeah, I think you have to be a bit careful.
That's what I thought.
Yes.
No, but I believe it's true. I mean that whenever X is locally compact, then the fact is true that such an inclusion is a compact mat in the category of sheaves. I guess more generally the claim is that unstable sheaves are compactly exhaustible, compactly assembled precisely if sobrification of X is locally compact or something. Anyways. Let's talk about this later, okay? I think I'm basically running out of time, but I'm on.
Take the unit interval and take
Sasha, what did he just say?
It's good with a little bit of discussion, though. That's why we're here. You better be guys.
Okay. Properties of dualizable categories. By the way, if you want to read about the proofs of this, like I think Sasha's paper contains quite a bit and some other papers, but we've also written this like script of lecture notes that you can find on my homepage together with Achim and now Phil. And somehow like everything is in there, maybe there's mistakes, but this is like where you can read up on all of that. Properties of dualizable categories. Let me just sort of mention a few that drop out of the proof that are really useful. C and D are dualizable. First thing you notice that X is compactly exhaustible, X in C is compactly exhaustible, if and only if it's omega 1 compact. Omega 1 compact. So this is useful. So after the fact that you know you're dualizable, then you're just talking about the same notions here. So generally, of course, this is not true. Second fact is that F from C to D is a functor. This is strongly continuous, which by definition means it admits a right adjoint that preserves colimits. So that's the definition, and then this is equivalent to F preserves compact morphisms. And it's also equivalent to, I guess, following diagram commuting.
I'm sorry, Thomas, don't you also need that directly with all the colimits?
Oh yeah, I guess I assumed somehow implicitly plus left adjoint. Okay, let's say F is already a left adjoint. So I was thinking somehow you start with a left adjoint functor and then you write out. Absolutely, thanks. And then I guess you can also somehow say diagrammatically, if you have a functor from C to D, F, and now I have this like int C, I have this J hat. And here you have this J hat here. And then you have int F here. I hope this is readable. And so what I want to say is this diagram commutes, and I guess there's a canonical mate transformation here, because if F like is left adjoint, then the diagram where it puts a case here commutes. So you get a mate transformation like this, and so this is an equivalent. So let me just say commutes. As indicating the mate is an equivalence. Okay, that's also a very useful characterization of these like strongly left adjoint functors. And I mean, you can just see that somehow it's not so hard to somehow show that this is equivalent to that, because you know by presentability we just need to check that the right adjoint commutes with filtered colimits, and then I mean if you contemplate what this means, then somehow commuting this J hat is basically implied once you preserve compact morphisms. Okay, and then of course you can make a definition. The definition is, I mean, here L dual is then the category of dualizable categories and strongly left adjoint functors. So in some sense, the correct functors between dualizable categories are those strongly left adjoint functors. And then, for example, you have one corollary from this description of preserving compact morphisms. is that the functor from sheaves X into B is strongly left adjoint. Strongly left adjoint. If the following. So what's the left adjoint functor? I guess I should say a left adjoint functor. So what's the left adjoint functor from sheaves X into D? So that's basically, sheaves has a generalized relations description as a presentable infinity category. It's generated by open X under the relations that like every open is a colimit of the Czech cover for any covering. So a functor like this is somehow basically a co-sheaf. So you have a functor from, it's determined by a functor from open X into D. That's a co-sheaf. Right, just meaning it's a sheaf in the op, I guess. And so this is just what a left adjoint functor out of sheaves into D is, such a co-sheaf. And so the statement, if this co-sheaf satisfies for U deep inside of V, by which I mean you can like sandwich a compact in between the induced map f of U to f of V is compact in V. And I mean, this doesn't quite follow from my characterization because somehow, I guess I said it has to preserve all compact morphisms, but these are like, I think in the proof we saw these are basically the generating compact morphisms in some technical sense. So this is enough. And this is a very useful description that, I mean, initially it took me quite some while to figure out actually. I was very happy when I learned this local description of compactly of utilizable categories and functors. Okay, I guess let me at least go through my list of properties that I want to give you.
I'm going to find continuity theory
In the remaining 0 minutes?
Yes.
Thanks to your... No, but I can say a word about it if you give me like 5 minutes. Sorry, can I have 5 minutes, Maxine? Okay. I was planning to. So okay, let me finish sort of giving you some properties. X to Y in C is compact if it lifts to a morphism from Jx, that's the Uneda thing, in int D to J hat Y. So in int C. And lift means, of course, once you apply the k functor here, you get back x and you get back j here. So that's a very useful description of compact morphisms. And then, I mean, once you have this description, you can even define a spectrum of compact maps, or compactly assembled maps, from x to y. You can define this to be just maps in this category int C from jx to j hat y. And you have to be a bit careful, right? I mean, there's a thing going on between property and structure. So I call them often compact if it is of this form, and then, I mean, there's a potential choice in listing into this here. That's why we call these compactly assembled maps, or I guess Joel Johnston called it wavy arrows. Well, this is a bit of a funny notation, but anyways, this is kind of how you can define the spectrum of compactly assembled maps, and that's very useful. Fourth thing, if X is a colimit over I, xi, is I compactly exhaustible? In the sense that I define for I having these like anti-symmetry, filtered, and no terminal object properties, then you can even understand what J hat is. J hat of X is then just the colimit over I of J of xi. So in other words, is the int object described by this filtered colimit? For example, if it's compactly exhaustible, which is a special case, then you know what the J hat does. So generally speaking, I find it somewhat hard to get a handle on this J hat, but sort of once you write an object in this form, then you know what the J hat does with it. Okay, maybe I skip some points. And let me maybe get back to 6. 6 is, I mean, I'm just skipping points here because I sort of wanted to say that, I mean, recall we have this Kalkin style resolution. This is maybe the most important part from the proof, that we have this int C omega 1, and then we have int of the continuous Kalkin category. And I guess for this functor C omega 1 to Kalk continuous C. And one useful thing is, and why this is called Kalkin categories, you can describe the mapping spectra in this Kalkin category. What you get is somehow the map in this Kalkin category, C, between Px and Py, to objects here. So this is actually given by take maps in C from X to Y, and you quotient by compactly assembled maps from X to Y. Right? This is kind of a formula I can prove playing around with these adjunctions then. And then you see this is kind of like why I guess it's called Kalkin category, because it's like in functional analysis, the Kalkin algebra, where you sort of quotient bounded operators by compact operators. And I guess my further plan was now to define continuous K-theory and to prove that colimits in PRL dual exist and are computed underlying. So let me just sort of, I mean, I guess I can say more about it in my next lecture tomorrow, but let me just give you like the one-line definition. What you do is like you want to define continuous K-theory of C, and what you do is you just define it using this resolution. So what you do is you have this resolution, and so you can write it as a kernel of compactly generated categories, and what you want to do is you want to define K-theory of a compactly generated category as just the K-theory of the classical K-theory of the small category here. So you just define this to be the fiber of K-theory of C omega 1 to K-theory of like Kalkin quantity C. And this is a small category which has countable colimits, so it satisfies an Einberg-Swindle. So this is actually 0. And so you end up defining it to be K-theory of the continuous Kalkin category of C omega of that. And as I say, somehow this is an extension of like K-theory. I think Sasha will talk about this. And I will sort of maybe go a little bit more with the definition if necessary tomorrow. And I also wanted to finish the proof that colimits in PRL dual exist and I can compute it underline. Okay, thanks.